Now we need to generate a reset signal and apply this to pin 21. If we look at the data sheet on what it says for the reset, it says pin 21 reset. Reset causes the processor to immediately terminate its present activity. The signal must be active high for at least 4 clock cycles. So we need to supply a high for 4 clock cycles. Now what we can do is we can use a little momentary switch. So if we push this and let it go, we could use this to generate a little reset signal. So if we connect that to this board here, if we push this down, we could hold that while the clock generates 4 pulses and then let go, and that we could use for a reset signal. So if we connected one side of the momentary switch to +5 through a 10k resistor, and the other side to ground, then when we push this switch, at this point of the switch, which is here, this could generate a high to low. The issue is that it wants the signal to be active high. So what we would need is actually the reverse of that. So what we could do is push it through an inverter. An inverter will change the signal so that the low will go to a high. And what we could use to generate that is a NAND gate. Now, why I'm not using an inverter, but I'm using a NAND gate, which is this here, a 74LS00. If I use that, then I can tie these 2 pins, 1 and 2, together, and we can actually invert the signal. Why I'm using a NAND gate will become more apparent, because eventually I want to go on to generate a single pulse. So rather than using the pulse signal coming from a clock, I want to be able to use a switch to generate a pulse one at a time, so we can step through clicking the button to see what happens on a single step. So that's why I'm going to use a NAND chip. So if we use a NAND and we can connect it in, then what will happen is the signal going from high to low, if we put it through an AND gate, it will actually invert it, and this low signal will go to high, which is exactly what we need, is our clock going high for 4 seconds. So let's connect in this LS74LS00 NAND gate, and it needs a power on pin 14. So if we connect pin 14 to +5, and pin 7 to ground, and then we can connect the connection here of the switch here at the bottom of the 10k resistor to pins 1 or 2, one, connect that to pin 2, and then if we simply connect pins 1 and 2 together, that will mean at pin 3 we'll have the signal we need. So we can connect this lead here to pin 3, which will be the output. So when we click this, this will go high, and when we let go, it'll go back to low. We need the clock signal, which we're generating from pin 3, 1, 2, 3. We've got the power connected. If we then connect a power supply of positive and negative, we can then bring in our microprocessor circuit that we built earlier. So if we connect the power supply positive and negative, this is the clock signal, and the clock connects to pin 19. Connect the clock to pin 19. I connect the reset to pin 21. Then if we power up our board, this should okay. Now it's actually running along in some unknown mode. So if we press the reset and hold it, the clock is generating the clock pulses, and hold this for 4 clock pulses. Then when we let go, the clock will generate, I think it runs for 7 clock cycles before it then goes through. And here we can see it's actually operating. So here the ALE is lighting to say the address is on the address bus. The green LED and the blue LED. The blue LED is indicating the red, and the green LED is indicating a write, with the blue indicating a read. And there we can see that the CPU is actually doing something. I've now provided the clock running at around 2 clocks per second, but it's hard to see exactly what's going on. The processor is certainly doing something. We can see via the red LEDs that the address is changing along with the data. We can see that the yellow LED is lighting, indicating an address is available on the address pins. We can see the blue LED, which is connected to the processor's read pin, that is reading something, and occasionally the green LED connected to the processor's write pin is trying to write. But even with the clock running at slowly at 2 clocks per second, it's difficult to see exactly what's happening. So let's look at the datasheet and see what it says around reset. Here it says that the reset is required to be high for 4 clock cycles, and it terminates what it's doing. It says the low going transition of the reset triggers an internal sequence for approximately 10 clock cycles, and after that it starts with an instruction at location FFFF0. That's great, as we now know what the instruction pointer does when it starts on a reset. And if we actually wrote some code at this address location, we could get the processor to start reading our code instructions. And that's the problem. The processor is starting at location FFFF0, but we haven't attached an EEPROM that contains any code. Normally, if we wrote some code, we'd enter this line by line. So if we wrote from code, for example, A equals 2, and then B equals 3, and then C equals 0, and then C was A plus B, then finally print C, we're writing our code line by line. And the first instruction, A equals 2, if that was at location FFFF0, the processor would read in that instruction. Then it would move on to the next address and read the next instruction, B equals 3, and so on. But we haven't connected any EEPROM with the code. And that's the issue. The processor thinks it's connected to read data, but these pins aren't connected. If you recall in the first video, we stated the processor uses an address and then looks at the data at that address. So if we place the first code instruction, A equals 2 at address FFFF0, this instruction is stored in the EEPROM at that address, and we can have the processor read out the code instructions. The processor has 20 address pins, and we saw that on the datasheet with address 0 on pin 16, Address 1's at pin 15, then it goes right through to address 14, which is on pin 2, and then addresses 15 to 19 are on pins 35 to 39. Also, it has the data, and it has 16 data lines, with D0 starting at pin 16. Therefore, the processor is resetting at this address FFFF0 address and is looking for the code instruction on its data lines. But at the moment, there's nothing on its data lines. So it's just reading random data. But if we could load an instruction on that data line on pins D0 to D7, then perhaps it might perform more predictably. Now here we have the instruction set. And here you'll see the instruction for no op, which is no operation, is 1001 0000. Therefore, if I set pin 15, which is D0 to 0, and the next D1, D2, D3 to 0, then pin 12, which is D4 to 1, D5 and D6 to 0, and finally D7 on pin 9 to 1, then when the processor reads the data pins, it will actually see this 1001 and then 4 zeros, which is that no op instruction. And although the no op instruction is saying do nothing, it might actually give us a more predictable operation. So I'll just connect these pins. Now, you can't directly connect the pins straight to ground. What we're going to do is connect them through a 1K resistor. So if I connect the first one, D0, and connect that to ground. Next one, D1, connect that to ground. D2 to ground. And finally D3 to ground. Then D4 needs to be a 1. So we connect this to +5 through the 1K resistor. The next two will be to ground to 0. And then finally, the very first one, D7 to +5. So what we've actually set on the data lines is a 1, 2 zeros, a 1, and then 4 zeros. So now, if we switch it on, will it run more predictably? So we need to run the reset for 4 clock cycles, and then internally for 10 clock cycles, it does a reset process. So there's the address lighting. Address lighting. So I don't know if you saw that, but what actually seemed to be happening was it's actually setting all those to 0, and the LED is lighting. So it's saying there's an address there. When the next time the LED comes on, it's actually setting 2. And then the next time the LED comes on, it's setting 6. And the next time the LED comes on, it's setting 8. So it's actually setting the pointer and moving the pointer from FFFF0 down to FFFF2, then FFFF4, then FFFF6, and then FFF. So it is actually moving along, and it's reading this no op instruction, and then moving on to the next instruction, which is the no op, and then moving on to the next instruction, which is the no op. We know, according to the datasheet, that the processor requires 4 clock cycles with a reset signal held high. And then after that, it will take 10 clock cycles where the CPU will begin execution at FFFF0. We've set data pins so that a no op signal, setting data pins D0 to D7 with the instruction of 1001 0000. But one other thing we can do before that is maybe use an Arduino Mega and use that to monitor the address pins. I've only been able to connect the last 4 pins, AD0 to AD3, and connect those to the 4 LEDs, which show the least 4 significant address lines. And I've connected the other 4 red LEDs to the most significant bits of address lines A16 to A19. And that was because to add 20 LEDs would make the breadboard too cluttered. So I'm having to assume those 12 addresses we didn't add red LEDs to are showing high, based on the fact that the datasheet information says on reset, the processor will set an address to FFFF0. But we could use an Arduino and monitor all 20 address pins and then display those so we can see what all 20 address pins are doing. We know that the processor uses the ALE pin 25, which goes high when the processor sets an address on those pins 2 to 16 and pins 35 to 39. So if we use an Arduino and connect it to all the 20 address lines and capture those on an ALE high, we can see what's happening. Here I have an Arduino, and I'm specifically using the Arduino Mega 2560, as this has multiple digital inputs and is more capable of connecting 20 of its data pins, which are along here and here, to the 20 address lines, so we can capture, and we can also capture the ALE signal. So I'm going to go ahead and connect the Arduino's digital inputs to the processor, and then connect the power and clock, reset the processor, and then see what the address lines are doing using the Arduino. I need to write a small script for the Arduino and use my PC to write that, but first I need to connect the 20 data pins, and I have a ribbon cable to do that. I need to connect to pins 2 to 16 and pins 35 to 39. However, as the address and data lines use the same pins, and I have these resistors connected to pins 2 to 9, I need to slightly rearrange the resistors so that they still have the no-op command of 1001 0000 on the data pins, but I can also get room to connect in my pins from my ribbon cable. Pins 10 to 16 are more easily connected, so there's no issue, but I'll just rearrange these 8 resistors off camera first. Okay, I've just rearranged those resistors off camera. I've still got the resistors connected as they were, with the first one connected to plus 00, then plus 5, then 0000. So we have 1001 0000 connected to the data lines. I'll just disconnect the reset and clock board just to get them out of the way, so it's not in the way of me then connecting the ribbon cable. On my Arduino, I've connected these pins 22 all the way through to 50, so I can connect these pins to the data line or the address lines on this side, and then this side I can connect the data lines there. So I need to just start connecting the data the address lines. So we'll start. Let's see. 0 and then 0 and 1, 2, 3, 4, 5, there, that's the address lines from address 016 all the way through to 14, and then I connect these ones. Okay. Starting at 15, address 15, which is pin 39. Okay, so that's all the address, the 20 addresses connected to my Arduino. I can then connect back in the plus rail, the negative rail, the reset, and the clock. Okay, and now I can proceed to connecting into the Arduino and writing a little code for the Arduino to monitor all 20 address pins and start the board. So I'll need to move on to my PC and set up the script for the Arduino. So let me now write the Arduino code, or as it's called in Arduino, speak a script. It opens with these setup and loop already created. If you just do File and New to create a new sketch. All 20 address lines of the 8086 are connected to 20 pins on the Arduino Mega, and I want to display each address line and then that in hex. So what I would expect to see is something like this. If I just open Notepad, I would expect to see on the screen the address lines coming out as this. But I'd like to actually then total that in hex. So I'd actually get not only the 20 address pins and what value they were displayed, but then the hex value as well. So that's what I expect to see coming out onto the screen. I'll use the sprintf function, and that allows printing and formatting. So I can pass a value in to be printed and converted, and then convert that to hex. I could use an integer, but actually an integer only holds 65,000 and 20 address lines is 1,000,000, so I'll need to use a long instead of an int. Final thing is we're using the ALE signal from the processor, as when that goes high to say there's an address on the pins, then that's when we can monitor the pins output there. That's because the pins both share the address and data lines, so I need to use the ALE signal to see when the pins are an address. So first of all, I'll need to define all 20 address pins in the Arduino, and I set these to pins 22 to 50 on even numbers, and then I use 51, 49, 47, 45, 43 as the A15 to A19. So I'll need to create a character array which will hold all the pins. Call that ADBR. And I set that to the pins it's connected to. So 43, 45, 47. So those are all the 20 address pins that the Arduino is connected to. Just check those look okay. And then, as I said, I'm going to use pin 2 on the Arduino for the ALE. I'll just call that ALE. Now, what I'll need to do is initialize those pins to be digital inputs. So the easiest way to do that is write a little loop. And within that loop, we're going to use the Arduino function pin mode. Okay, so that will just loop round, setting those 20 pins to be inputs at the start of the loop. We'll also need to do the ALE. And I'm going to use an interrupt so that we can capture the ALE and read the pins. And using the rising edge. And I'm going to use the serial monitor, so I'll need to set that up as well. And set their baud rate. Okay, so that's the setup. And then I'll need to write this on ALE function that I've written in here. So that'll be and within this, as I said, I'm going to create a total. So I'm going to put this in as an unsigned long called total. Initialize that to 0, and then I need some output. So make that output, say 20 characters should be more than enough. Next, it'll need to loop round and read all the pins. So again, we'll create a little loop. So this bit will actually read the pins. And they can be either a 1 or a 0. And then to the serial monitor, print this out. And then my total, what I'm going to do is, as I said, I want to create a total, and that's going to read each bit and shift it along and give me a total. And then I'm going to give some spacing. And then I'm going to use this, as I said, the sprintf function. So that string that we defined here, output that character string. And if I then convert that to hex, so that's the format for that. It's better. Pass in the total, and that should then print me out that hex value. And then print line and print out that string. Okay, let me see if that builds. Okay, it's got an issue there. Oh, I forgot the sign I put in was a semicolon. Okay, what have I got wrong there? And values of this. Oh, comments. Okay, so that's compiled, and I'll also need to connect ALE. I'm going to use pin 2 on the Arduino. Pin 2. And we extended the ALE out to that yellow LED. So the ALE comes on this wire here. So I should be able to connect there for ALE. Also, I need to have a common ground. So I connect the ground on the Arduino to ground on the board. And now I can start the script. Now the sketch is compiled. What we need to do now is upload that to the Arduino, power up the board and press the reset. So let's upload that. So here it's uploading, done uploading. So it's now uploaded to the little Arduino Mega. We can power on the board. And then if I start up the serial monitor, I need to check that this is set to the same baud rate as I've set here in the initialize, 57600. So that's correct. I'm getting some rubbish data coming out at the moment from the board. So we're going to clear that and then press the reset and hold for the 4 clock seconds. So let me clear that, press reset. So I clear that again, press reset, hold for 1 to the 4 clock cycles, let go, should then initialize and it then should start. So we can actually see the address is going just as it says on the reset from the datasheet. FFF0, FFFF2, FFFF4, FFFF6, FFFF8, FFFA. So the data sheet says, following a reset, the 8086 operates normally, beginning instructions at FFFF0, and then we can see it increments forward from 0 to 2 to 4 to 6, etc. Why is it not going 0, 1, 2, 3, 4, but going 2, 4, 6? Well, that's because the processor is reading 16 bits, so it has to move the pointer on in groups of 2. We have set on the data lines a no-op instruction, so the processor just moves on to read the next address, and as we've used resistors to hard code 10001, 0000, then no-op instruction, it's just moving on in sequence. The problem is it's going to be really difficult to try to write code in this small section of FFFF0 through to FFFFF. And if we look at that datasheet, it says in this small region should be used to code a jump instruction to another part of memory where we can write our code. So the next step will be to code a jump statement at FFFF0 location, rather than the hard-coded no-op, which I've done through the resistors. So to do that, I'm going to now add an EEPROM chip, and the one I've chosen is the 27C512, as this uses a 16-bit address, and we can code in the jump statement to that EEPROM. So that's what I'll try next, and connect that up.